In this video, I'm going to be deriving a relationship between the height of a ball in a rotometer and the volumetric flow rate of the fluid going into that rotometer. So first, I'm going to talk a little bit about what a rotometer is to help us conceptualize a little bit. So basically, all a rotometer is just a pipe with a ball in the middle. And so I'm going to define the diameter of this ball to be d naught. And then generally there is a fluid flow going into the bottom. I'm going to label this as position 1. It's our starting position. But we have a flow rate into the bottom of this rotometer. And the fluid is going to kind of flow up around the sides of the ball and then back to the top of the pipe. So our first position is going to be this starting position, position 1. The second one I'm going to define at the area between the ball and the pipe, and then our third position is just at the top. So kind of depending on the flow rate going into the rotometer, this ball is able to kind of move up and down. And so what we're going to do to derive this expression is I'm going to first start with the force balance on the ball inside of the fluid. So we're going to have the ball is going to be at equilibrium, and since it is, the weight of the ball is going to be equal to the pressure forces on this ball. So I'm first going to start with getting the an expression for the weight of the ball. So weight is just mass times gravity. But in this problem, we don't have the mass of the ball. We just have the density. So to kind of get the weight of the ball, it's going to be the density of the ball times the volume of the ball, which is just pi d naught cubed over 6. This gives us the volume of the ball, or this gives us the mass. Density times volume is the mass times gravity. And then we also have the buoyancy force on the ball that's kind of counteracting this weight of gravity. And so since we've defined the weight or the force due to gravity as positive, the buoyancy is going to be negative in the opposite direction, or positive going down. Gravity is positive going down, so the weight or the buoyancy force is going to be acting in the opposite direction, going up, so it's going to be negative. So to get the buoyancy force on the ball, it's just going to be the density of the fluid times the volume displaced. We have the density of the fluid times the volume displaced, which is just the volume of the ball, times gravity. And so to kind of clean this expression up, I'm going to write it over here. It's going to be the density of the ball minus the density of the fluid times pi d naught cubed over 6 times g. So that is the effective weight of the ball in this problem. And now, since the ball is in equilibrium, we're going to have to balance it out with the pressure force, and those two are going to be equal. So taking a look back at our rotometer, we're going to have two different pressures on the ball. We're going to have the pressure at location 1 that's pushing up against the ball, and then the pressure at position 3 that's pushing down against the ball. So to get pressure force, it's just the pressure times area gives us the force. So for our pressure force, it's just going to be P1 minus P3, which is our net pressure, times the force of a cross-sectional area. So for this, it needs to be a flat area, so we can kind of calculate it and add up all the forces normal to it. So our area that I'm going to choose is going to be kind of a circle in the middle of our ball, so that way it's normal to the both the pressure forces going up and down. So that area is just going to be pi times d naught squared over 4. And so, like I said before, these two forces are going to be equal to each other, so I'm going to set them equal. And now we can go ahead and cancel a couple terms. So this pi is going to cancel with this pi. This d naught squared is going to cancel with d naught cubed to just leave d naught. And then I'm going to multiply both sides by 2. So this will become 2, and this will become 3, just to kind of simplify a little bit. So if you notice in our equation here, we have P1 minus P3, but we're really more interested in location 2 for this problem. So if we kind of look at location 2 and how the fluid flows by it, it goes from a very small area, very small cross-sectional area, this kind of small bit between the ball and the pipe, to the entire pipe diameter, or the entire pipe cross-sectional area, relatively quickly. So we have a sudden expansion, and when there's a sudden expansion, there's no time to recover pressure. So because of this, the pressure at position 2 is going to be equal to the pressure at position 3. So I'm going to go ahead and substitute this into the equation. And then rewrite it and clean it up a little bit. So on the left side, we have P1 minus P2 now. I'm going to multiply this 2 to the other side. So we're going to have the density of the ball minus the density of the fluid times 2 d naught g over 3. So this is our force balance for the problem. And now since we have this, we can go ahead and apply Bernoulli's equation to this problem and continue from there. So Bernoulli's equation is P2 minus P1 over the density of the fluid plus the velocity at position 2 squared minus the velocity at position 1 squared over 2 equals the frictional heating coefficient. But for this problem, we're going to assume that there's negligible frictional heating and that the change in potential energy as the fluid moves up the pipe is also negligible. So that way we can set this equal to 0 and kind of make things a little bit more simple. So our next step is I'm going to kind of massage this equation a little bit, so we'll be able to incorporate our force balance into this equation. And so the first step for that is I want to rewrite the velocity at position 1 in terms of the velocity at position 2. How I'm going to do this is I'm going to use the relationship that the velocity at position 1 times the cross-sectional area of position 1 is equal to the velocity at position 2 times the cross-sectional area of position 2. I can use this relationship here because the density of the fluid isn't changing throughout the problem. So here I'm just going to solve for V1 in terms of V2. So it's just V1 equals the velocity at position 2 times area at position 2 divided by the cross-sectional area at position 1. So now we can go ahead, plug this in here, and kind of continue to massage our equation. So I'm going to go ahead and move this term to the other side first. So on our left side, we're going to have V2 squared over 2 times, because once we plug in for V1, we're going to have a V2 squared in this term, and then 2 in the denominator so we can pull it out. So we're going to have this multiplied by 1 times our cross-sectional area at position 2 over the cross-sectional area at position 1 squared equals, since we move this to the other side, it becomes P1 minus P2 over the density of the fluid. And so looking back at this area term, we have the cross-sectional area at 2, which is extremely small, over the cross-section of area at 1, which is relatively large. So we have a small number over a relatively large number, and then we square that so it gets even smaller. So this term essentially is negligible, and we're going to equate it to 0. So now from here, we can go ahead and solve for V2. So we have the right side of the equation, which is P1 minus P2 over the density of the fluid. Kind of give myself a little bit more room here. So to get rid of this 2 in the denominator, just multiply by 2. And then we'll take the square root. So from here, if you notice, we have this term here, our pressure at position 1 minus the pressure at position 2. And we also have the term again up here in our force balance equation. So we can go ahead and plug this in here. And I'm just going to kind of go ahead and write that off to the side because we'll use it again later. So our expression for V2 is going to be square root of, we have 2 times 2, so it's going to be 4 times the density of the ball minus the density of the fluid times the diameter of the ball times gravity over the 3 times the density of the fluid. So now that we have this equation, I'm going to kind of erase the work and then talk about the next steps. So here we have an equation for the velocity at position 2, but the problem that we're trying to solve is getting an expression for the change in height of the ball in the rotometer with respect to the volumetric flow. And we have neither height or volumetric flow in our equation. So now we kind of need to incorporate both of those. I'm going to start by start with the volumetric flow. I'm just going to call it Q. And to get the volumetric flow from the velocity, it's just going to be the velocity times that cross-sectional area at that position. So we have our equation for velocity. We derived that already. Now we need to define the area. So we're looking at this area here, this small little bit in between the ball and the tube. So to get that area, it's just going to be the cross-sectional area of the pipe minus the cross-sectional area of the ball. So to calculate this, I'm going to define D as the diameter of the whole pipe. And so this is just equal to the area, which is the cross-sectional area of the pipe, pi d squared over 4, minus the cross-sectional area of the ball, which is pi d naught squared over 4. So now we have volumetric flow rate incorporated. We need to incorporate height. And kind of how we're going to think about this is I'm actually going to redraw our rotometer. How I drew it isn't exactly accurate. Usually there is a slight taper on the pipe. Like if you look at images of a rotometer or maybe look at one on eBay, we did that during our class, you can kind of see a slight taper of the pipe. It's wider at the top and a little bit skinnier at the bottom. So I'm going to kind of redraw it like that, exaggerating a little bit to make it easier to see. So the taper is usually not this big. It's just a slight one, but this makes it easier to see. So we've got our diameter, and it's going to change with respect to height. Kind of as height's low, we have a smaller diameter. As height increases, our diameter gets larger. And so this can be represented by a linear expression, basically y equals mx plus b. So I'm actually going to write that down to kind of help me work through it. So y is our dependent variable, and that's what's changing. So it's just going to be the diameter. M is the slope, So it's the rate of change in this problem of the side of the pipe. And this is something that's usually given, or you can measure it, or if you create the pipe, it's a specification that you put in for the pipe to be fabricated. So this is a known value. So I'm just going to leave it as m. Now x, our independent variable, that's just going to be h, because the diameter is changing with respect to h, and that just leaves our intercept. So our intercept, it's going to be where the height equals 0, so it's basically the lowest point in the pipe, down here. But what is the diameter at that point? If we think about it, there's a ball. There's the ball inside of this rotometer, and it can move up or down. If it moves all the way up, it just shoots out the pipe. But if it moves all the way down, it kind of wedges itself against the pipe, and there's no space between the wall pipe and the ball. So the smallest diameter that it can be is going to be just the diameter of the pipe, which we have as d naught. So now that we kind of have the rate of change for the diameter of the pipe, we can go ahead and plug it into our equation. So we're going to have Q equals V2. I'm going to pull out this term since it's here and here. So we're going to have pi over 4 times d squared. So d squared is just equal to this equation squared. So m squared times h squared plus 2m h d naught plus d naught squared, and then we have minus d naught squared. So from here, it's kind of just algebra. These two cancel out. And then if we take a look at this term, like I said before, m is usually an extremely small number. And like with our ratio of the areas before, when you square an extremely small number, then it's basically negligible, so we can equate it to 0. Here as well. And all that's left is to kind of rewrite this and plug in our velocity equation. So I'm going to do it nice and big right here. Give myself some space. So we have Q. Our constants, which is this pi over 4, 2m and d naught. So 2 pi m d naught over 4. So this just becomes a 2. And then we can go ahead and plug in this equation here, which is just 4 times the density of the ball minus the density of the fluid times the diameter of the ball times gravity divided by 3 times the density of the fluid, all raised to the 1/2 power, times h. So this is the expression that relates the relative height of the ball inside the rotometer with the flow rate. And what's kind of cool about this equation is all of these terms here are constants. So it kind of shows that there's a direct correlation between the volumetric flow rate and the height of the